Hey everybody, so this is the third video on gravity, and we're just going to talk about gravity on Earth in particular. So we know that you exert this gravitational force on everything in the universe, and everything in the universe exerts this gravitational force on you. So here you go, well, apparently you're jumping right now, but you're on Earth. But we also know that the sun's out here, and then some other like distant stars. And if all of these things are attracting you with a force, so force, the sun's pulling you, some distant star, and Earth, then why don't you get ripped apart into pieces? Right, because we don't really see this. Right, and then your like arms floating out over here, your leg gets pulled down to Earth, your other arm's floating up in the air, your other leg's floating around, right? You don't get torn apart, and this is good. And in the last video, we saw that when we threw in some random numbers, we found that the force between you and that distant star was about 6 times 10 to the negative 122nd newtons, which is a really tiny number, and it's so close to zero that our bodies wouldn't even be able to feel it. So the reason we don't get torn apart by the gravity between us and everything, and likewise those things don't get torn apart because of the gravity between it and everything, is that usually there's one force that kind of overrides them all. And most of them are really small, and the one that we feel is the one that's the strongest. So for us, of course, that is the force of gravity between us and Earth. So if I redraw this, and this time you won't be jumping, maybe you're just actually standing here on Earth. Let's go ahead and calculate the force of gravity between you and the Earth and you. So we'll just write out Newton's equation for gravity, and go ahead and plug some numbers in here. So the mass of Earth is about, well, let's do it the right way then. So I guess the mass of Earth is really more like 5.97 times 10 to the 24 kilograms. And then your mass will be 60 kilograms. Okay, and then the one thing we're missing is the distance between you and Earth. And if you're standing on the surface of Earth, you might be thinking, well, I'm kind of on Earth. There's not really any distance between us. But for calculating distance with a sphere, you always go from the center of that object. Not always, but generally from the center of that object to you. So the distance actually ends up being the radius of Earth. So the radius of Earth is 6.378 times 10 to the 6 meters. Okay, so now we have all of the information that we need, so we'll just plug it in. So 6.67 times 10 to the negative 11 Newton meters squared per kilogram squared times 5.97. Oh man, this was a bad idea. Alright, we're writing somewhere else. Note to self, plan better with space. Okay, we're going to write it down here. 6.67 times 10 to the negative 11 Newton meters squared per kilogram squared times the mass of, let's do the Earth first, 5.97 times 10 to the 24 kilograms times your mass, 60 kilograms, all divided by the radius of the Earth, 6.378 times 10 to the 6 meters, that whole thing squared. Alright, we plug that all in and we get a number, and it comes out to 587-ish newtons. So that's the force of gravity pulling you down and pulling the Earth up to you. And the important thing to see here with this equation is that the higher the mass, the combined masses of the objects, right? So you multiply the two masses together, the bigger that number is, the stronger the force. And the closer you are together, the stronger the force. So since Earth is fairly massive and you're really close to it, the force is quite strong.